I saw this the first time. My eyes were open and big. I could not close it in 5 minutes.
Yeah.
Wow! So, Steve, have you ever seen anything like this?
No.
Beautiful.
This is Bob Duchesne's Wild Maine. On today's show, we're going back in time. About 450 million years. Everything we are now is because of everything we were then. If you looked at a map of Maine geology, it'd be a very complex picture. It'd also probably be wrong. The official state maps were about 32 years old, and that's just not good enough these days. It's time we took another look under the soil, under the glacial till, and look at rocks. These rocks have quite a story to tell. We've had a very violent past. Today, I'm surrounded by geologists who know how to read these rocks. We're going up in the woods, way up, somewhere west of Ashland, and we're going to drive roads that only bears, moose, and loggers know about. Bob Duchesne's Wild Maine is brought to you by Hammond Lumber, Bar Harbor Whale Watch, Napa Auto Parts, and EBS. We'll start at the beginning. There was this Big Bang, see? And it sent clouds of hydrogen and helium through space, and a lot of that coalesced into stars and planets and other stuff. About 4.5 billion years ago, one of those was our own sun, and we were one of its planets, the third one from the sun. Eventually, the Earth hardened up, or most of it did. Continents and oceans formed. And if that was all that happened, there wouldn't be much of a story to tell. But it turns out those continents could move, and they'd collide and break apart. And there would be volcanic eruptions and sea level changes. And the Earth as we know it is vastly different from what it was. But if you know what those differences are, you can find good stuff, like minerals and energy. So God made geologists who know how to read the clues and find the good stuff and avoid doing bad stuff, like polluting groundwater, or ruining rivers, or even making sure our well water is drinkable. We're on a mapping project today, trying to get a better idea of where everything is, when it's hidden beneath the forest. Basically, we're looking for places where the top layers have washed away or been scraped away so that we can look at the bedrock and see what's there.
Good morning.
Good. How about yourself? Hi, Bob Duchesne.
Tyler Pollock. Nice to meet you.
Steve Pollock.
Hi, Steve.
No relation.
Mile 6 Gate, one of the entries to the North Maine woods. If you're going in for work, fun, or adventure along the Pinkham Road or Reality Road west of Ashland, your day would start here. There are 8 of us altogether, and 6 of them are geologists, or soon will be. My chief guide is Dr. Bob Marvany, Maine State geologist. Dr. Shenjun Wang is professor of geology at University of Maine in Presque Isle. Caleb Ward is an undergraduate student and is interning this summer as his assistant. Dr. Steve Pollock is a retired professor of geology at the University of Southern Maine, and his assistant is Tyler Pollock, who's no relation. Basically, they've divided up a big section of forest up here, and they're searching for unusual bedrock. Bob Marvany, the state geologist, is supervising this mapping program under a state grant. We're about to take a look at some of their astounding discoveries.
See ya. Yeah. Bye-bye.
You can't stop at a North Maine Woods gate without a little small talk.
That is a new guy from, I think he's from South Carolina, either South or North Carolina.
Oh,
and he just bought a salmon pool camps.
Oh, he did?
Do you know salmon pools?
No, I don't.
Hellstrom?
No.
Yeah, he just bought salmon pool camps.
Ah.
Yeah. People are buying our sporting camps like crazy. Another guy just bought Machias Lake.
Oh, really? Wow.
Yeah, sporting camps are all from out of state.
Uh-huh.
Yeah.
So they don't know any better.
I think they, you know what I think it is? I think they got more money than we got up
Yeah,
here.
well, that might be it.
Because times are hard up here.
Yeah.
Times are hard.
Yeah.
So you're going to spend your day in the woods, huh?
We are. Is that all right?
Where are you going?
Wherever Chunzeng leads us.
We're past the gate. Shengzhen has a map on the hood of the truck explaining to Bob Marvany where we're going. I'm paying attention because not only don't I know where we're going, I don't even know where we are. You may notice that Dr. Wang has an accent that isn't quite down east. It's more far east. He's from central China, but he's now one of the most popular professors at the University of Maine, Presque Isle.
Okay, so we're here right now.
Yep.
This is the fork. This is the American Realty Road.
Yeah.
This is the Pinkham Road.
Okay.
So we'll go here first
Okay.
to see the basal conglomerate,
Yep.
then back, then going to Jack Mountain, going to Pingham Road, drive to this area.
Okay.
So
that's the plan for the day.
Yeah, that's the plan for the day. We'll drive this way. So you have big picture.
Over the course of the summer, 2 crews have been searching for geologic features that will tell us what's underground. Shenzhen has been searching one side of the quadrant. Dr. Steve Pollock has been searching another. Finding features is one thing, but matching up similar features is another. In order to map what's happening underground, they're trying to find similar deposits and ledges so they can connect them up on a map. Maine's bedrock in this area was formed in many different ways. Some of it is from lava flows, some of it from lava eruptions, some of it from a time when this part of Maine was under the ocean. You can use rocks that are hundreds of millions of years old to know what happened where, because how those rocks were formed tells you what the conditions were when they were formed. The plan is to visit some of their biggest discoveries, and we're headed to the first one right now. Somewhere on a side road off the reality road, at a place I couldn't find again if my life depended on it.
All right, stop number 1.
So this is the Sibumuk Formation, sandstone, mudstone, slate, or whatever you call it. And basically, Sibumuk is sandstone, siltstone, slate. Somewhere there is limestone. Then there, see that ledge there? That's the conglomerate. Okay, so the contact is right there. And there's a pit there. The pit is mostly the conglomerate. So that side, that's conglomerate. So we are at a contact between the regular Sibumuk sandstone, siltstone, and the conglomerate there.
Stop number 1 is an important discovery. 2 things: if you're going to map something, every map needs boundaries. Where does one bedrock deposit begin and the other one end? Where is the contact point between where rock laid down by lava begins and where sedimentary rock laid down by the ocean floor begins? You need to find places where these two are right next to each other. You also need names for these deposits so you can name them on the map. In this case, the team uses place names based on the actual locations where they're discovered, so one of the deposits we're looking at now is named Sibumuk. We'll hit another one later named Munsungan. This deposit is a conglomerate. When you look at it, it's like a whole lot of different rocks got mashed together in some kind of soft medium. The medium could have been lava or mud, but it's older rocks mixed into something wetter and basically hardening into new rock.
Okay, so what is it you're doing?
Yeah, I'm trying to get my hand lens out so I can have a look at this slate here. It's so this is one of the common slate units across northern Maine. It's surprisingly light weathering right here. Usually it's fairly dark, so I'm just looking closely at the minerals to see if it probably has a lot of feldspar in it, which is why it's weathering this white color. But it's pretty thin weathering zone. Only a few millimeters thick right there that it's weathered. So this basal conglomerate is really interesting though, because that's marking the bottom of the unit, and it's the erosional remnants off of the older rocks that had to be exposed for some period of time. So that's what we should go have a look at.
Okay.
It doesn't take long to realize that what geologists do more than just about anything else is to hit rocks with a hammer. Sedimentary rocks in particular, like sandstone and shale, were laid down in layers and compressed into rock. Those layers aren't that hard to break apart, and you can get a look at what's inside. On this particular piece of shale, Bob Marbany is wondering why the outside part of this shale is so white when shale is usually a lot grayer. It must have something in it that causes this appearance. Rocks often have minerals embedded throughout their structure, like feldspar, iron pyrite, mica, or other silicas. These are like fingerprints and allow geologists to match these rocks with others that were created in the same way at the same time out of basically the same materials. Dr. Wang says this all happened here sometime during the Devonian period in Earth's history.
So I roughly remember when Devonian is, but put that in English. Wait, give me a few million years one way or the other.
Around 416, 400.
Yeah, that was that's the bottom of the Devonian.
To 300...
360?
60 million years ago. It's between 450 and 360 million years.
Yeah, so this was ocean bottom that long ago.
Yeah, that long time ago.
And that's why it's a conglomerate of us.
Well, and so this is the material that first eroded off of the older rocks, and there's all
kinds of stuff from the basement
of
Yeah,
of
look at all.
materials in here. These green slates or cherts, are they?
Cherty,
Yep.
chert.
Yep.
Yeah.
And then some very fine grained.
That's
those look like
that's a diabase.
diabases. Okay.
There are lots of diabase in the basement and basalt.
Yep. And
So
then
whatever
these
you see
red-
from the
red
basement
this
that you see
here?
there.
shirts.
Is
That's-
that more chert?
Yeah,
Yeah, that's
red. Lots
some
of
of the
red
red.
chert.
Yeah.
You see that?
Quite a
The red
Quite a
chert
variety.
makes this to be unique because we also have conglomerate in this area, lots of them. But this has lots of red chert. That one doesn't have. So there's a difference.
So all this would have been mixed in the ocean bottom
Yeah,
and
this is
then sort of congealed into
this
the
is
rock.
shoreline that time. Then the sea level is rising, right?
Mhm.
Then you have when sea level is rising, that means for the same place it's farther from the shoreline, right? Then if farther from shoreline, the large polygons cannot move that fast.
Right.
You know what I mean? Only
do.
smaller ones.
Yeah,
Then that's why
right.
you see the small, finer.
Yeah, well, it's like
finer
silt in the
poly-
river.
Yes.
Yep.
Yeah.
So it gets sorted out pretty quickly, a short distance from shore. So this is immediately near the shoreline, where there's a lot of energy.
Now get this. We're looking at rocks in the woods, somewhere along a logging road west of Ashland. There's a ledge here that's made up of conglomerates. That is, it's older rocks embedded in newer rock, something like you might see in an inlaid mosaic, for instance. We know that older rocks are just up the slope. From all this, geologists can deduce that right here, an ancient river washed down these rocks into the sea right at this very point, a point that is now 1,000 feet above today's sea level. How do they know they were washed down by a river? The embedded rocks are rounded, just like the rocks you'd find in a river today or along a pebble beach in the ocean, worn away into a rounded shape. And how do we know what this zone was like? The silt and smaller rocks are carried further by the current, whereas the heavier materials just drop out more quickly. Bigger rocks in the conglomerate give way to smaller rocks below, so you can see what the grade was like even that long ago.
And this shows us that whole process was going on here, 400 and some odd million years ago. There aren't too many places in Maine where you can progress right from the older rocks through a basal conglomerate into the younger rocks. So that's why this is important to see.
That's Bob Marvany, Maine State geologist. Dr. Senjin Wang is geology professor at University of Maine Presque Isle, and there are other geologists here on the team as we're mapping a big chunk of the Maine woods up here west of Ashland. If you know what rocks are down there, you can know what valuable resources are also down there. Or conversely, you can know what other resources you need to protect. This is Bob Duchesne's Wild Maine on Sports Radio 92.9 The Ticket. This is Bob Duchesne's Wild Maine on Sports Radio 92.9 The Ticket. I'm with Maine State geologist Bob Marvany and a team of scientists up here in the North Maine woods. We're somewhere off the reality road, standing on a rock outcropping that tells us what happened here 400 million years ago. State maps made 32 years ago show that this area should be full of igneous rock, basalt, or some kind of lava-type rock.
At this moment, I would say that's completely wrong.
We now know this find right here indicates that our maps need some work. Not surprising, since our science and technology has improved over the last 3 decades. But why does it matter?
So if you were looking for valuable minerals, for instance, and you had a volcanic deposit, that'd be maybe something that indicates potential. You get to a conglomerate like this, and there's not as much potential?
In this part of Maine, that's true.
Yeah.
Right,
Yes.
right.
And
So-
in this part, that's why you see the color here. This color. This is the old, the basement.
Yeah.
The older rocks covered by the younger ones. But later on, they are folded. That's why these guys, you see them here. Then you see the younger ones here.
So if you were prospecting, you'd get here, and you'd look, and you'd drive on.
Yeah, right. You
Right.
come into those slates and say, "Well, I'm not in the right rocks yet," and keep going this way to try and find the volcanoes.
The cover doesn't have volcanic rocks. Only the older ones, they have volcanic rocks.
We moved on to another site, on another obscure logging road off the beaten track, somewhere out west of Ashland. This location also has an outcropping of conglomerate rock. That is, a bunch of older rocks were carried away and eventually settled into something softer, like, mud, where the whole mess eventually became rock. So if you've been with the show for a few minutes, what did you learn about how to read this like a geologist?
Yeah, fantastic.
Well, it's different conglomerate than what was down below, because it's got more red in it. What's the story?
Well, so they're more red class. It's just the particular rocks that were eroding when this material was being deposited.
So same process, but basically a different.
Yeah, just slightly different.
Yeah,
so
okay.
So the rocks that are eroding have a lot of variety in them, and that's what we see, a tremendous amount of variety in this conglomerate here in terms of the stones that are embedded in it. And the other difference between here and the last outcrop was that a lot of these clasts are much better rounded than they were at the other one. So these have been carried just a little farther by water and the interaction of water and all these cobbles. They bang together and it's a big slurry of material, and the softer rocks get rounded much more quickly. So really great exposures here.
Mm-hmm. So on the ocean floor, this all sort of melded together into one giant rock?
Right, so a big, a massive layer. This goes well off into the woods here. A massive layer of material. So this would be probably a pretty steep submarine canyon type setting, maybe, where there's a lot of material funneled into a narrow area to produce this thickness of conglomerate.
And then it got upraised by seismic activity?
Oh yeah, this is all, yeah, so this was, of course, submarine at the time it was deposited, and now we're, I don't know, 1,500 feet above sea level. So in that time there's been a huge amount of tectonic uplift. And of course, at their maximum, the Appalachian Mountains in this area were probably 15,000 feet tall. So we've eroded off 2 or 3 miles of material to expose what we see here, and all that was transported out into the Gulf of Maine.
One of the things this team of geologists is really looking for is contact zones. That's where rocks laid down by 2 different events come together. Among other things, those are the borders you need for mapping, but the contact also tells a story. 2 layers may have collided, or a fault may have tipped one layer over the other, or conditions at one point may have been different, such as the edge of an ocean. Dr. Senjin Wang.
And geologists always try to figure out what happened in the past, telling a story about 400 million years ago, like this. Then how this came here, like that.
So a contact area is where 2 different stories came together?
Yes. Yeah.
So the break between the older rocks and this conglomerate would represent how many millions of years? 50 million years, maybe? 465. And this would probably be around 415, maybe. If we found the contact where this conglomerate sits right on the older rocks, that line represents 50 million years of time. Just that.
Right there.
More than that.
That's right.
Actually, it's
more than that.
Yeah,
probably,
well, we don't have the ages yet.
Yeah, right.
That's another story.
Yeah.
Mm-hmm.
This area is so important, but so far nobody has ever absolutely dated the rocks here.
Well, you're not doing it by carbon dating, so how do you date it?
Yeah, fortunately, most igneous rocks contain a little bit of zircon, the mineral.
Chemically very stable.
Yeah, and zircon will trap atoms of uranium in it. And over time, naturally occurring uranium will decay to lead. And so measure the ratio of uranium to lead, and you know how long it's been there.
So easy.
Yeah, it's that easy.
The problem is, it's that expensive. It costs roughly $2,000 to measure the age of one rock. One thing I'm wondering, we're standing in a place that was once ocean, and probably pretty deep at that, too. I know the glaciers depressed the earth, and that when they melted, Maine was covered by a lot of salt water till the land rebounded. So 400 million years ago, was the land depressed by something, or was there just more ocean?
I don't think it was more ocean, but what happened in one of these episodes when the Atlantic Ocean was first opening was that there was very rapid ocean floor spreading. So new ocean floor was being created at a very rapid pace, much quicker than today, and that young oceanic crust is less, it's hotter, and so it's less dense, and it sits up higher, and it just basically displaced the ocean basin water to where it flowed over the continent of North America and deposited thick sequences of limestone across the central part of the United States.
Right.
And that was because that spreading was so rapid that there was a lot of young ocean crust that basically was more buoyant, displaced a lot of water that then had to flow over the flat, continental areas.
I'm just considering where to invest for future oceanfront property.
Yeah. Mount Katahdin might be good. It won't be too long before it's oceanfront. The right things are going.
Katahdin Island.
Stay away from Machias.
Yeah. Well, right after the last glacial episode, the sea came all the way up to Medway. So Mount Katahdin was practically oceanfront property back then.
Bob Duchesne's Wild Maine is in the woods somewhere west of Ashland. I'm surrounded by geologists. Bob Marviny is the Maine State geologist, and he'll set up the next mystery. When lava comes out of the earth, it cools into rock. But can geologists tell whether that rock cooled in air or water? Well, of course. But how? Stand by for the answer. This is Sports Radio 92.9, The Ticket. This is Bob Duchesne's Wild Maine. Saturday mornings at 9, Sunday mornings at 8 on Sports Radio 92.9, The Ticket. I'm in the Maine woods on a logging road west of Ashland. Bob Marviny is the Maine State geologist, and he has oversight over a geology mapping project going on up here, taking place on forestry lands. The logging roads get us into interesting places where outcroppings of ledge can give us clues to what Maine looked like 400 million years ago. There was a lot of volcanic activity up here at that time, but at other times there was ocean covering the same land. So I put the question to you before the break: can geologists tell if lava cooled in air or water? The answer is pillow rocks.
Pillow basalts, here we are. See the rounded shapes of this form right here, like that and like this. So that confirms to us that this was volcanic activity beneath the ocean, because as soon as the lava is extruded into the water, it cools rapidly and it forms kind of a crust, and it makes these blobs that then accumulate on a slope or on the bottom and then harden over time into this characteristic shape of what we call pillows. When you see them well exposed, they look like stacks of pillows.
It's this one, right?
Well, let's get a jack on here.
Yeah, I'm just breaking the bolts before we jack it.
Good idea.
We've just turned onto the Pinkham Road on the way to our fourth stop. If you want proof that we're actually doing this, here it is. It's only 10:30 in the morning, and we have a flat right next to the Machias River Bridge up here in Aroostook County. So that would make a great setup for a joke. How many geologists does it take to change a tire? In this case, one. Caleb Ward is the undergraduate college student who is interning with Dr. Wang in the study, and he's flattened so many tires in this road already that his best time for changing a flat is 6 minutes, or so he says. This one takes about 15.
So I guess I'll be going slower.
Yeah.
As we get back into the truck, I'm actually sharing the seat with Caleb, and we're about to hit an area of basalt, which is a volcanic rock. All these rock types we're seeing have to be mapped, which means they need a name. So, Caleb?
It's called the Chase Brook. So each geological feature is named after a memorable landform in that area. In this particular area, it's Chase Brook, which comes down through here. But right now, that's what we're in. We're on this side here, and we'll come up into this spike of basalt, this basalt flow like we saw before.
Yeah. So basalt flow is the same as a lava flow, essentially?
Yeah.
Yeah, in this radio show, I dumb down everything so not only the audience, but the host can understand what's being talked
Yeah,
about.
of course. It's important to make all this stuff accessible to everybody.
That's right.
Well, it's everybody's
it's
real life and stuff, so we want everybody to understand what's going on.
Oh, yeah, the audience picks it up quick. It's the host that's dumb as a rock. Our fifth stop is astonishing. We're on a side road off a side road somewhere off the Pinkham Road, and I couldn't tell you where we were. Seriously, not only don't I know where we were, but what we're now looking at is incredible. It's jasper, the red semi-precious stone that can be polished up and used in jewelry. Sometimes you can find little ones on a beach, and there's even a jasper beach in Machiasport. But this is no ordinary jasper. This is a huge chunk, the size of a card table, embedded in volcanic rock. Dr. Senjin Wang discovered it, and he could still barely contain his excitement.
This is when there's an explosion, right? Rocks are broken, then fragments, explosion. Then, interestingly, this is very rare. This is big blocks of fragments are jasper, red jasper. Very beautiful, very high gemstone quality jasper. So we keep this side as a secret. We don't want the public to know. We want the people here come here to knock the rock. So
Well, that's okay. This secret will never leave this room.
yeah, surround is finer fragments. We call tough or lapilli, depending on the size.
So how did that happen?
I just told you, volcanic explosion. There was a volcano around this area back to that time, and the eruption. The volcano was probably more under submarine in the water, and so then there was an explosion here. Volcanic explosion or eruption. Well, why jasper here? That's a good question.
That was the question.
Where's the jasper from? Right.
Right.
That's what the question I want to know the answer for. So then this is one place we found. There's another place with the same kind of rock like this, but that one we have to go into the woods, but this one we can just drive here.
It's my favorite kind.
Yeah, this is a pretty
It's
pretty
gorgeous.
rock, very pretty. It's rare, very rare. You see large chunks of jasper inside a volcanic breccia. You probably cannot find this from any other place in the world. When I saw this the first time, my eyes were open and big. I could not close it in 5 minutes. Wow! So, Steve, have you ever seen anything like this?
No.
Beautiful.
At this point, everybody has assumed the geologist position. All of them are lying face down on the rock, peering through a magnifying glass, looking at the tiny minerals and crystals that give jasper its gemstone-type quality. Jasper can come in many colors, but typically a lot of silica gives it a red color. Also, as geologist Steve Pollock told me, when you have a lot of silica, volcanic eruptions can be more explosive, throwing boulders like this one a long way. Our next stop is also where volcanic eruptions threw stuff. But in this case, these are the kind of sharp volcanic rocks that Indians could shape into tools and arrowheads. It's one of the major reasons this mapping study is underway. Not only are we interested in the value of what might be underground, but we're also very interested in the archaeological significance of places like this, hidden out here in the Maine woods. Tools made from Maine stone were traded by the tribes, and you can find artifacts all over the eastern United States that started out as rocks in places just like this one. Dr. Bob Marviny is the state geologist, and in a moment we'll cover exactly why a mapping of the Maine woods is so important. This is Bob Duchesne's Wild Maine on Sports Radio 92.9 The Ticket. This is Sports Radio 92.9 The Ticket with Bob Duchesne's Wild Maine. I'm in the Maine forest with the Maine state geologist who is leading this program, but the actual field work is being conducted by additional geologists who are here with us today, showing us what they found. It's time we get the inside story on why this mapping project is important.
Well, Bob Marviny, I don't even know where we are, but the volcanoes knew because they threw all these rocks here.
Right, so we're somewhere out in the woods west of Ashland, and in a section of rock that has a lot of volcanic, indicates a lot of volcanic activity that's pretty old, probably 450, 460 million years ago. This was a very active place.
And right around here is a lot of rocks that were thrown from some of this volcanic activity here. It's all loose, scrabbly stuff. I would have thought that when the ice ages came through, they'd just scrape all this and carry it away.
Well, some of it has been. We're probably, it depends on which side of the hill you're on. On the northwest sides of hills, they would generally be scraped flat, but on the southeast sides, the glaciers actually grab onto blocks and just pull them off and leave a pretty rough surface.
Mm-hmm. When I was growing up, and this has to be, let's say, 50 years ago, I would have learned that we have basically three types of rock: sedimentary, igneous, and metamorphic.
Right.
That was the old wisdom. Has that wisdom changed at all?
Well, those are still the three classes of rocks, but we need to break them down in much more detail. So, for example, the igneous rocks, we divide into volcanic rocks where lava actually flowed out on the surface, and intrusive rocks where the lava was in the crust, never made it to the surface, but cooled into rocks. So that's dividing those igneous rocks down, and these are volcanic, so they flowed out on the surface. A lot of them actually subaerial, below, on the land surface, but some that we've seen today actually flowed out under the ocean. Mm-hmm. And so we can look at the nature of the rocks, and we can divide them into those that float out on the surface and those that float out beneath the oceans.
We've mentioned the word chert a lot during the course of the tour so far this morning, and I'm not exactly sure what that means.
Well, chert is a kind of a common term for this very fine-grained rock that is so fine-grained, actually, that with the naked eye you can't see crystals in it. It looks like just one color, one texture, and it's very glassy. When you break it, it produces very sharp surfaces. And there's a couple different ways that true chert and these chert-like rocks can form, all in volcanic settings. One is the actual volcanic activity can produce a very quartz-rich rock and very fine-grained that we call chert, and the other is through a process of it's done chemically. Mm-hmm. Yeah, a different way.
Yeah. Now, all rocks essentially are put together by some kind of mineral, or minerals are formed in rocks, or what is the difference between a rock and a mineral?
So rocks are formed of minerals. Mm-hmm. So every rock you pick up, even if it's too fine-grained to see grains in it, they are made up of minerals. And some rocks, it's very easy, like a granite, you can see all the different minerals in it: quartz, feldspar, the micas. So every rock is made up of minerals, and it's the types of minerals and how they came to be together in the rock that help us classify rocks into the different types, and then subdivide them into more detail.
A lot of the formations of rocks, a lot of the rocks themselves and the different types would be formed by how much heat was applied, how much pressure was applied, what was the baseline mineral mix in it to begin with, so that you produce all these rocks that I couldn't possibly pronounce. Yeah, but that's how it happens.
Right. So in Maine, if we look across the whole state, we have mostly igneous rocks and mostly metamorphic rocks. So the igneous rocks we already talked about; they're from molten magma, lava. Mm-hmm. The metamorphic rocks are those that they could have been igneous rocks, they could have been sedimentary rocks being laid down by water, mostly sand and gravel.
Gravel, shale.
Exactly. So the metamorphic rocks are either an igneous rock or a sedimentary rock that have been changed by heat and pressure. And so most of the rocks from actually south of Aroostook County all the way across the state of Maine are those metamorphic rocks. They were originally deep ocean sediments that were subjected to high heat and pressure when the plates that make up the crust of the earth collided to form the Appalachian Mountains.
Mm-hmm. So why map all this? And let's start with the fact that the official state maps right now are a little bit on the elderly side.
Right. So we have a state geologic map, covers the whole state. It's a wall-sized map that was put together in 1985. So that's a few years ago now. And some people would look at that and say, well, it's all done. You've mapped everything. Mm-hmm. Well, in fact, we know that many areas on that map were filled in by geologists in just a few days of working along dirt roads like we're on in northern Maine here, just seeing what they could see along the roads. So there is actually a lot more detailed mapping that should be done. And there's reasons to do it other than to just look at, to understand the geology and how it came to be. There are resources here. One reason we're mapping in this area is because of archaeological resources. The cherts were exploited by Native Americans for their stone tools, and we are certain that there are more cherts than have been mapped previously, and that's what we're discovering in this work. And they're also hosting new archaeological sites that hadn't been recognized before.
Now, in terms of what the actual commercial value might be today, we have not abundant valuable metals in the state, but we have some.
Right.
We have famous mineral deposits and gemstone deposits. Right. Do you map out the state to figure where those are, or what's the reason for doing it?
Well, that's one of the other justifications for doing this work, is that we only know the very basic geology here. And we know there are mineral deposits in similar rocks in Maine and in neighboring New Brunswick, and if we map them out in more detail, that'll form the foundation for additional exploration work. And in fact, some exploration geologists are still interested in Maine.
And as it happens, I think America, especially, I'll say corporate America, is interested in pursuing a variety of values in their land. It used to be around
Right.
here, it was trees.
Right.
And trees was it.
Yep.
Nowadays, you see a lot of wind power going up on mountaintops. Mm-hmm. You see water withdrawal going because we have such a good supply. And there's always the discussion about what minerals might be available to us commercially.
Right. So there, and it's clear in my mind and to exploration geologists that I've talked to, is that Maine is really underexplored in terms of metallic minerals, precious metals, and other commodities. I mean, nobody even looked for rare earths back 40, 50 years ago when there was pretty active exploration programs in northern Maine, but they're hugely valuable to our modern society right now. Every one of our mobile gadgets has rare earth elements in it.
Let's hit the pause button right there. We know a number of things already about the resources under our feet. We know that we don't have the right geology for natural gas, so we don't have much potential for hydraulic fracturing or fracking in Maine. We know that we have incredible groundwater resources, some of the best anywhere. We know that we have some precious metals, and there's been recent controversy over whether it's possible to get at those deposits without harming those water resources. But we haven't talked at all about rare earth metals. These are 17 elements you've probably never heard of, like scandium, promethium, erbium, thulium. Many of these metals are essential in modern electronics and electric car batteries. China has most of the known deposits, so if major deposits turn up anywhere in America, you can bet there's going to be some interest. What do we know about the potential for rare earth metals in Maine? I'll ask next. This is Bob Duchesne's Wild Maine on Sports Radio 92.9 The Ticket. Welcome back to Bob Duchesne's Wild Maine. This is Sports Radio 92.9 The Ticket, but today we're a rock station. And the rocks we're looking at are about 450 million years old. I'm in the North Maine woods, somewhere west of Ashland, with Maine State geologist Bob Marvany and a team of geologists mapping out what's going on underground there. We're doing that by finding little pieces of ledge in the woods that aren't covered up by trees and topsoil, and we're matching them up with other ledge in the area to figure out what's going on beneath our feet. Bob Marvany is explaining why we're doing it, and someday the answer may be rare earth metals, the heavy elements that go into our modern electronics and batteries.
Do we have any rare earth that we know of in the state, or are we just completely lacking?
There are places, mostly in the gemstone district of western Maine, that has potential. Mm-hmm. We know of some. They're small, but again, not terribly well explored in any way.
Yeah, when you talk to universities, they wish they had more jobs around for geologists. Is that because we just don't have enough people pursuing the commercial value of it or the scientific value? We just don't have the opportunities in the state? Or?
Well, so the metallic mining hasn't been active, and it's probably not going to pick up to be a major source of jobs in the near future. But the real focus in Maine geology for students coming out of school would be to work in the environmental field, looking at, spills or cleanups, solid waste, siting of facilities, dealing with the geology so that they're sited properly, so that we don't have these problems down the road would be the way to go.
Well, and what Maine has a lot of is water.
Yes, right.
And that's the resource that nobody wants to mess up.
Right.
And since that travels underground, you have to site all of your activities appropriately.
Yep.
That takes some knowledge of geology and what's underneath the surface. And
absolutely. And we know there are commercial opportunities in groundwater itself. So, and we have plenty of public water systems that use groundwater resources, and they employ geologists to do those investigations to look at what a safe yield is from an aquifer. And then we have, as we know, we have commercial uses for groundwater as well, bottled water and others.
Which is really very valuable.
Yes.
And a good source of jobs in the state.
That's right.
And so if we're going to ever produce this kind of natural resource jobs, the front line of that is often the scientists and the geologists in particular who are aware of what's happening on the ground and can make sure that a project goes forward without harming other resources.
And it takes very careful, detailed investigations. And there's a very strong regulatory environment around that.
And as you point out, it's been like 32 years since we mapped the state, and that was just a rudimentary map.
Right. So there's a lot of ground that really could use the kind of detailed work we're doing here. And so we're selective. We look at priority reasons to go to a location like here because of potential archaeological resources, potential mineral resources. Other parts of the state we're mapping the superficial materials, the stuff left over by the glaciers, because they make the best aquifers in the state. And we're also looking at the glacial muds that were deposited at the end of the glacial episode because they're prone to landslides. So geologic hazards is the other reason we need to do more detailed work.
When you're doing archaeological research in particular, you're really interested in where the chert is, where the resources would have been of interest to the Native Americans 5,000 years ago.
Yeah, right.
If you were more interested in the metallic resources or gemstone resources, and you're driving around the woods, what would you be looking for to be a telltale clue?
Well, we would be looking for specific volcanic rocks, and it's usually a combination of several types of volcanic rocks that erupt in an area, and they're usually submarine. So this is lava flowing out beneath the ocean, and when it's the right combination of a couple different rock types, it's probable that it was a long-term process that allowed metals that were over a broad area to be accumulated through these geologic processes into a deposit. And it's rare. It's rare that happens, but so we're looking at the volcanic rocks primarily to try and sort that out. When you find streams and waters that have the byproducts of a sulfide deposit, that's usually quite noticeable. Right. Manganese is something that shows up in well water on a somewhat regular basis. Yep. We know we have a problem with arsenic in the state. Right. And we detect all that in water. So how much does water give us a clue about what the landscape is like? It does. We definitely do a number of things. You can use water sampling, usually out of wells, for example, and then stream sediment sampling, actually going into small watersheds, sampling the finer grained sediments and doing chemical analyses to see how much copper, how much lead, how much zinc might have been in that. And that leads you then, if you design it right and have kind of sediment samples that come from a small catchment of streams, then you can identify prospective areas where you might want to do sampling of the soils and then eventually sampling the rock and maybe drilling to find minerals. I think one of the things that's most fascinating about our process so far today is my understanding of how the smaller stuff is carried further. So during a volcanic eruption of some kind, the ash goes the furthest, the smallest particles not quite as far, the larger rocks not too far from the mountain. Right. Same thing when material is being carried to the sea. Exactly. The fine stuff washes further. So when you see all these deposits in the woods, can you kind of read that? Well, that's right. And so we look at the different rock types, and we sort out the deep sea marine sediments from the near near shore, very coarse conglomerates, and then also the very explosive and large explosive volcanic rocks that have the large clasts in them. Those would be proximal to wherever, right near the source of this volcanic activity. So you sort through all that, and you can begin to map out, you know, the extent of these various deposits, and then interpret from that where the volcanic activity was the most intense and so forth.
And you're actually mapping back like 450 million years.
That's right. These are old rocks. Yep.
450 million years. Boy, time flies. And this hour in the woods with Bob Marbany, Maine State geologist, has also passed quickly. This is Maine, formed by fire and ice, shaped by oceans, and right at our feet. History is preserved right there. Except for this show, which is preserved for re-listening at 929theticket.com. All shows are archived right there. Bob Duchesne's Wild Maine returns next Saturday morning at 9, Sunday morning at 8, brought to you by Hammond Lumber, Napa Auto Parts, Bar Harbor Whale Watch, and EBS on Sports Radio 929 The Ticket.